Unfortunately, in the previous lecture, I'm not sure when it cut out. One of my memory cards seems to only go up to 26 minutes. So I'm going to go over some of this again. Apologies if it's in the previous video, and I'm a bit up the wall, so I can't wait to check because I have to upload the video to actually view it. So apologies if you can skip on to the next page. I think if you've seen this already. Okay, let me go. So what we're saying here is we can show that for a sample of size n equal to 10, that 95% of the sample means lie within a certain number, 2.262, a number we got from this table, which you will see again, standard deviations from the mean of the sample means, which is the population mean. The standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size. So basically what that's boiling down to down here is that if I set up this thing, now the funny thing is you don't know this number. It exists theoretically, but we don't know what it is, and we don't know sigma. It's theoretically we can calculate it, but actually we're trying to estimate it. But theoretically it's there. And so what you have here is the probability that if you take a sample of size 10 from this population, so say there's millions of rods and mu is the average length of the rods, and you take a random sample of 10 and you look at the average of those 10, the average length, the probability that it becomes between these two numbers is equal to 95%. So 95% of sample means fall between these two numbers. Now look at some of the places that it might land. Say it might land there, you might be very, very lucky. So I'll call that sample mean 1. This one, sample mean 2. And then we'll look at this one, sample mean 3. Okay. Now the first thing to say is the probability that you're very far away, so the distance between, say, sample mean 3 and the population mean is big, and the probability that the difference distance between the sample mean and the population is big is 5%, because there's 95% of you being close. So we'll do 1 first. So we have to realize there's a 5% chance. I'm going to say that the sample is inaccurate, because what are we trying to do here? We're trying to take a sample of rods, say 10 of them, to estimate the average of all of them. There's a 5% chance that you're out here. So 5% chance inaccurate sample. Now all I want to say about sample means 1 and 2 is that the distance between them and the population mean is smaller than this delta x bar. So with 1 and 2, distance between, say, sample 1 mean, sample 2 mean, and mu is less than this delta x bar. Now n is 10, 2.262 we got from a table. The sigma we don't know, but we can estimate it using the sample standard deviation. So while we don't know, we can do it roughly. Is less than this. And what is the probability that this happens? This bit, 95% chance. So there's a 95% chance that the distance between the sample mean and the population mean is small. Okay, this is what we're talking about. But we just one caveat down the bottom. Not in reality, we've no idea what the population standard deviation is, but it can show that we have a good estimate. So I think I have an analogy here on the thing. I think it's nice to understand this. I think it makes things easier. But here's just a way of thinking about it. So suppose you've got a dartboard, and suppose you're trying to get the bullseye. Like the bullseye is like the population mean. Well, what you want to do is you want to set up a region into which you're 95% likely to fall if you're trying to kind of throw at the population mean. And let's say, for argument's sake, this is 10 centimeters. So if the probability that the dart is within 10 centimeters of the bull, the center, then distance, I mean, it goes both ways. If Cork City is within 10 kilometers of Glenmire, Glenmire is within 10 kilometers of the city. So the probability that the dart is within 10 centimeters of the bullseye is equal to 95%. And so 95% of the time, the distance between the dart and the bull is less than 10 centimeters. And this is how we're going to kind of set it up. We're going to look at not the distance between the bull and the dart, but the other way around, which of course is equal. Okay, so we end up with a formula here, which you'll probably be using. Suppose that a sample is taken from a population with a standard deviation of sigma. If it is found that the sample mean is x bar, so that's like throwing the dart, then the following is what's called the p% confidence interval. So this is like, so you throw, basically what you do here is, like you don't even know where the bullseye is in this thing. So you throw the dart, you put a circle around the dart, and 95% of the time you catch the bull. Similar story here. So what you do is you put, instead of putting like the, like this distance around the population mean, which you don't know, you do the sample, and you put those bars around the sample, and say 95% of the time you catch the population mean. So that's the idea. Whenever you throw a dart, there's a 95% chance you're in here, and if you put circle around your sample mean, there's a 95% chance you'll catch this. This is basically the idea. Now I probably shouldn't repeat that again, but this is what we'll strive on. We'll do the calculations from now on, but that's the full explainer of what's going on. So here T depends on N and the level of confidence. We'll see that that's from the table. We'll do examples. And the population standard deviation can be approximated as S. Note the interpretation. On the p% confidence level, the population mean lies within here. So you have a confidence that the population mean is in there. Now there's a very kind of tricky, messy probability statistics argument here about, like say if I make a measurement of the length of the rods. So I say x bar, say I get 8.01 meters. Then I calculate this and I get a range of values. Say I get 7.98 meters up to 8.04 meters. And I am, say, 95% confident that the average length of all the rods is in this interval. The reason we say confident rather than probable is the following. So the population mean is an actual number, and it's either in this interval or it's not. So the probability that the population mean is in here is either 0 or 1. And that's a subtlety. Now, I think it's stupid by them. If I was them now, I wouldn't do that. And instead I'd say, before you take a sample, there's a 95% or whatever percent chance that you will catch the population mean in this interval. But anyway, that would put us different to what other people do. You just say you're 95% confidence in there. Now you have to be aware there is a chance when you do the sample, even if it's a 99% sample, there's a 1% chance that the true average of all of them is either bigger than this or smaller than this, and you just have to run with that. We can't be certain, and the more certain you are, the better your ISO level or whatever. Okay, so let's do some examples. In measuring the thickness of a certain material, so maybe these are plates that are being produced, metal plates, the 5 values were recorded here. Find a 99% confidence interval for the thickness, and this really is the population mean thickness. So the average of all these metal plates that ever were made and ever will be made, as long as it's under the same thing. So let's calculate this interval, sample mean minus a number of sample standard deviations. So first of all, we calculate the sample mean. So you take the average of these, just the normal average, and you get 10. So the x bar is 10. That bit's okay. Now we need to approximate sigma with the sample standard deviation. So we'll calculate it. So I can write down formulas and you can do whatever you want, but I strongly recommend the following method. So we have the data. I'll write down the data. So it's like the xi are 9.98. See, the reason I like this method is because you can't do it without understanding what the standard deviation actually is. Now, you probably will have an opportunity to use software, and then like you'll just press a button and the number will come out, but you don't know what it means. Whereas if you do it this way, you do know what it means. Now, of course, if I give you way more data, you'll have to use the software. Okay, so what I recommend you do is you look at the deviations. So how spread out are these from the sample mean? And the sample mean is 10. So this one is 0.02 away from 10, 0.02 away from 10, 0.01 away from 10. So like measuring how far away the data points are from the average is measuring how spread out the data is, which is exactly what the what standard deviation is about. This one is 0 away, and this one is 0.03 away. And the plus or minus doesn't matter because you're going to be squaring these. So now you square these. So I get 0.0004, 0.0004, 0.0001, 0 squared of course is 0, and 0.0009. And now what we do is we do S is equal to, you add up the deviation squared and divide by 1 less n minus 1, which in this case, well, let's just we'll write the 5, and then you do minus 1, and then you do the square. Now, you don't have to do this in an exam situation, so don't be too worried about it. You can figure it out slowly if you need to. And this is equal to, so I add up these numbers, 0.004, I'll get 008, 009. Could go a bit faster here, couldn't I? That's adding up. I didn't bother adding up 0. Divided by not 5 but 4, and taking the square root of that, and I'll take 4 significant figures here, is probably loads, 0.02121. Okay, and that approximates the population standard deviation. Okay, now the t-value. So the t-value is, we have a sample size of 5, so the n minus 1 is equal to 4. And what are we looking at here? We're looking at, okay, it's a confidence interval, so it's going to be like this kind of a thing. We're looking for a range of values into which the population mean is going to fall. So if we're talking 99%, we're talking about 1% in the two tails. So we're talking this number here. And we go down and we get 4.604. 4.604. Now you'll see that what happens is, as n gets smaller, these numbers get bigger. And so that means that like the range of values where you think the population mean is very, very big. Yeah. Okay. So put in the numbers, 10, 4.604, that was our t-value. There's the estimate of the population standard deviation divided by the sample size. And you get these numbers, 9.956 and 10.04. So we're 99% confident that the average of, just by looking at these 5, that the average of all of them is between these two. Now you might notice that none of them are actually bigger than this or smaller than this. But the sample size is so small that we can't be much more definite than this. And this is a kind of phenomenon that you'll see, a situation you can't get a large sample, you just can't be very, very sure. Okay, so we'll do another question and just outline it. So this is the density of a material, so this might be a concrete situation or something like this. We've no units here, which isn't a great question. Find 99% confidence limits. So again, we'll calculate this interval. So we find the average of these, no bother. We approximate this using, maybe I'll do this myself down here. So let's look at add up the deviation squared divided by, well, here just 6, so it should be 5. So this will be, so looking at the deviations of this is 0.02 squared. The next 3 are all 0. And then the last one is 0.01 squared divided by not 6, but 6 minus 1. Because otherwise, this number underestimates how spread out the data is. and we get to maybe 4 significant figures. And what do we got? 0.02 squared plus 0.01 squared divided by 5. We're getting, oh, equals 0.01. Ooh. What's going on here then? Oh, there's two of these yolks, sorry. Plus 0.01 squared. There's another one there. So 0.1095. Well, 0.01095. You can see it's a bigger number because there was more deviation there than I thought. So the t-value, so here we're talking, color pen. So the n is 6, so the n minus 1 is 5. And we're talking here, again, it's a 99%. So 99% in here, you're talking about 1% in the tails. So look, area in two tails, 1%, 4.032. So we get that 4.032, and you get these two numbers here. So you're 99% confident that mu is in this range between 3.0, whatever is 4 significant figures is loads, just by looking at these 6. Now there is a chance that the population mean is bigger, in which case you were very unlucky. There's the 0.5% chance that these are particularly small or not dense, and there's a possibility that the population mean is actually smaller than this, 0.5% chance, and that is that these were particularly dense. Okay. Now we're going to have a look at what happens. So there's something we mentioned previously, said that with a big sample, it's going to be better because, well, we said those peaks. Let me see, what am I talking about, peaks? So a large sample, this is very, very narrow, and that means that most sample means are close to the population mean, so it's more accurate. But when n is bigger than 30, now actually here I'm going to kind of slightly go against this, but I'm going to give you the option, and usually I'm going to recommend that you do it right. So the idea is that once you get down to n bigger than 30, which is kind of from here on in, they say that the t distribution is very, very like the normal z bell-shaped distribution. So the idea is that these numbers are somehow similar. Now I'm actually not mad on this because they're not similar. And what's worse is that if you use the z numbers instead of, say, if it's a size, now like if it's n equal to 50, you should be using 49, but you don't have 49, just use 50. You just use the closest thing. The 2.678 is a bigger number, so what you're going to do is you're going to be less precise, which is what you should be doing. Like, so, like you're saying, oh, I think the concrete has strength between 10 and 12. And that's a big wide range, like going down to 10, maybe that's really, really weak. But if you use Z, maybe just use 10.5 and 11.5, and you're like, well, that's not really right, is it? So I actually think you should use the T rather than going to the Z for these large samples, but let's have a look. So the situation is for large samples, which means bigger than 30, the T's are approximately the Z's. Now, one thing is true, when n is bigger than 30 in the DAS not group, we cannot easily calculate sample standard deviation. Well, you can with software, as you will be using. Yeah, there it is. Following the analysis goes true. So suppose that a sample of size bigger than 30 is taken from a population. So the sample mean is x bar, and the following is the interval. So this is using z's instead of t's. And I'm just going to say, just use t. And I mean that. I suppose the reason is maybe in a book you'll see this thing, oh, it's bigger than 30, we'll just use z. I don't think it's actually a good idea. As mentioned above, the z values are t for any going to infinity. There's actually a line of values for these in your t tables. Okay, yeah, we're actually going to run with the t's, I think. Yeah, let's run with the t's. Okay. A road engineer measured and recorded the period of time that's supposed to be between resurfacing of 50 randomly selected third-class roads in one particular county. this study yielded a sample mean of 6.75. So of the 50 roads they looked at, and they said, oh, maybe when was the last time he was resurfaced, or what was the distance between the last two resurfacing, they got an average of 6.75 and a sample standard deviation of 1.8. That means like most of them are kind of between roughly 4.5 and whatever, 9 years. Hence calculate a 95% confidence interval for the population mean resurfacing period for this particular county. Right. So all we're really going to do is we're just going to do this formula with t's. That's all. So we could use z rather than t, but t is better. So we have the sample mean is given to us at 6.75. We know that the population standard deviation is approximately the sample standard deviation, which is also in the question, is 1.8. We know that the sample size is 50, so all we have to do is find t. So what we should do is go down to n equal to n minus 1, which is 49, but that isn't there. So we'll just go to 50. And what is the confidence level? 95%. So that means 5% in the two tails, 2.009. So 49 we want really, but we can't. 95%, so 5% in the two tails, 2.009. So we calculate the numbers. 6.75 minus t, what did we just say? 2.009 times sigma, which is approximately s, over root 50. And you see this 50 is big, and so it's making this much narrower. So if you want to get an accurate sample to estimate a population mean, what you want to do is you want to get a large sample. But as we said, we have to look at the small ones because it's not always possible. Now the roads are funny because possibly they could have just looked at every single road. Well, we're usually thinking of big data where you can't measure everything. So let's write it out. It's 95%, was it? Yeah, 95% confident that the average resurfacing period of all the roads in the county, mu, is in. Now I'm just going to calculate these two numbers. 6.75 minus 2.009 by 1.8 divided by root 50. I'll do four significant figures. 6.239 and then plus 7.261 years. So it's reasonable to say that the average is definitely well, it's between these two, and you're getting it down to 1 year, even though like there could have been roads that were 10 years, 4 years, but remember this is the average, and we're 95% confident that the average is between these two. Now there's still a 5% chance that the 50 roads we looked at were good ones that were resurfaced quite frequently, and what that means is that the true resurfacing, the mu, the average of all the roads is actually bigger, or we could have gotten bad roads, whatever. Okay, so now this next question is an absolute beaut, and so it'll be one lecture on its own.